Okay, all right. Welcome everyone to APCTP Colloquium. Today's speaker is Professor Zohar Komargodski from Simon Center for Geometry and Physics. It's a great pleasure to have him, and let me briefly introduce him. So he's a very renowned theoretical physicist who works on quantum field theory, high energy physics, and also interface between condensed matter and high energy physics. So I think for a working physicist in this area, we'll have no need of introduction of Zohar because any high energy theorists will encounter his work. So he had most famous of his work includes proof of A theorem, and he has worked. It's not just it's a very deep result about renormalization group flow. And he has many other many interesting work regarding the deepening our understanding of quantum field theory, which is a universal language of theoretical physics. And he has received many awards. One of the most notable one includes the New Horizon Physics, the New Horizon in Physics Prize by the Fundamental Physics Prize Foundation. And I think I don't need further introduction because everybody should know him if you are a physicist. So without further ado, let's welcome Zohar.
Thank you so much. I am very humbled by this introduction. But yeah, I'm very, very happy to have this chance to speak to you. I would like, because it's a Zoom session, so for me not to talk to the screen, I'll be very happy if people stop me at moments where there is some discussion to be had, either questions or comments or insights. So please stop me at any point. I'll try to go slow at the beginning and maybe at the end, depending on the time, I'll increase the speed. We'll see. So the subject is defects in quantum field theory. It's a very large subject. I'm not going to cover the whole subject. I'm just going to cover some recent developments that I particularly like. And I've been working on that mostly with Gabriel Cuomo and Aviar Aviv Moshe and Mark Mezei, and recently also with Ofer Aharoni, Philip Boyle-Smith, Diego Del Mastro, Marieka Van Biest, and David Tong. I'm still working on this. There are a few other things going on, but I've invested the last almost 2 years in developing this subject. So I just wanted to give you some summary of what is going on in this field of defects. So let me just start with some very trivial introduction that is probably not needed in this audience. So quantum field theory is now a universal language in physics, as Jay once said. In every department in physics, this is the workhorse. This is one of the leading frameworks and languages. It appears in statistical mechanics, condensed matter, elementary particles, and cosmology, and so on. And somehow it became so important because it's somewhat analogous to calculus. So many different problems end up being equivalent or amenable to the same techniques in quantum field theory. So many problems are ultimately discrete, but there is some limit in which they become continuous, and that's why it's a little bit analogous to calculus. So there are many possible discrete problems in mathematics, but there is sometimes like a continuum limit, and calculus is a very powerful language to discuss problems which admit a good continuum limit. And in the same sense, quantum field theory has emerged like the leading framework to treat a lot of different problems for that reason. So I'm going to go over some examples that are familiar. It's just an introduction, and it has nothing to do with defects. So one problem which is very classical, it has no H-bar, it's not quantum, it's just a combinatorial problem of a spin up or down, a classical system of spins, where you try to sum over all the possible configurations of the spins, and you pay some energy price if two spins are not aligned. So if you pay some price J if they're misaligned, and you sum over all the configurations, this is the famous setup of the Ising model, which was developed probably more than a half a century, well, 70 years ago, or even more. And this is a classical problem with no H bar. But famously, this problem admits a continuum limit. And in the continuum limit, quantum filter is important, even though the original problem is not quantum. Another problem that's much closer to perhaps daily experience is the phase diagram of water. So we live somewhere here in our daily life, and the vapor phase and the water phase are separated by phase transition. That is what happens when we boil water in a pot. But actually, ultimately, these two phases are not distinguishable. You can go continuously from one to another without ever encountering a phase transition. And there is a very interesting critical point. And this critical point, again, the original problem has nothing to do with quantum mechanics. It's just water. But this critical point, again, quantum field theory is the correct framework. Another problem that you might have heard about is the confinement-deconfinement transition, in which quarks are liberated. So quarks are normally confined into hadrons, and there is some temperature above which they're liberated. And let's say in SU2 Yang-Mills theory, this phase transition where quarks are liberated is described by, again, some quantum field theory. And of course, all of these instances will be exactly the same quantum field theory, which is the notion of universality, that the very same set of equations can describe such vastly different systems. Finally, nowadays in the condensed matter community, it's very popular to think about zero temperature quantum phase transitions, not driven by thermal fluctuations, but just by quantum fluctuations. So there could be a system of quantum spins, not classical spins. So these are some Pauli matrices. And as you change the Hamiltonian, they could go through some interesting phase transition, which is called the quantum critical point in condensed matter. And again, this is described by quantum field theory. So all of those four examples are described by the same Landau-Ginzburg type quantum field theory, where there is some order parameter m, and we just write some functional of the order parameter, expanding in derivatives and in powers of the order parameter. And this and in this setup, one can discover an important gapless theory, massless quantum field theory, that is actually giving the correct experimental answers for all of those four different problems in the one model. So at the phase transition, it turns out that all of these systems have a very enhanced symmetry, which is the conformal symmetry. This happens in all the examples I told you before. The symmetry is enhanced to some SO4, 1, which is the conformal group. And then there are local operators, and they have scaling dimension delta, which in statistical physics are related to the critical exponents. The 2-point functions of the order parameter are fixed in terms of the scaling dimensions of the corresponding local operators. And for instance, in this 3D Ising model, which is the example that I just went through, these are the two lowest lying eigenvalues of the scaling dimension. So the magnetic field has dimension 0.5, the operator has dimension 0.5, and the energy field m squared has some dimension 1.4, 1.3. And these are some constants of nature that we actually don't know fully. We don't have a closed form expression. So quantum field theory is emerged as a universal language because you see that it unifies completely different. This is from the Department of Statistical Physics. This is perhaps from statistical physics or fluid mechanics. This is from high energy physics. It's the phase transition that liberates quarks. And this is clearly a condensed matter system of spins on a lattice. And all of them are described by the same equation. And at the end of the day, the critical exponents are the same for all of those four different systems. And that's why quantum field theory emerged as such a supremely useful language, because many things can be encompassed in the same set of equations. Are there any questions about this quick introduction for why quantum field theory reigns supreme in so many different areas in physics. Oops. Okay, so let's continue. So if you look at the history of the field, there has been probably thousands and thousands of important papers studying local operators. So this would be in the language of, let's say, the spin system, some local perturbations that you make a product of two spins and you study correlation functions of this product of two spins across different points on the lattice. So there has been a lot of work on measuring such local operators and their correlation functions. Because of this very large symmetry at the phase transition, SO41, the correlation functions are constrained by the conformal group. And the people have invested a huge amount of work in developing these theoretical constraints, and also a lot of work on the numerical results on the scaling exponents. At the end, these results are numerical. We don't have an analytic closed form. So people have invested a lot of effort in understanding local operators in quantum field theory, because this corresponds to averaging products of spins across different lattices, and you can compare with experiment. This is a very mature field. But
simple question.
Yes.
Yeah. So the number of symmetries may not be sufficient, and what kind of constraint can be given to correlation functions, to constraint correlation function?
Okay, so the
More
simplest
concrete, yeah. Yes.
Very good. So the simplest constraint is that the two-point function of local operators is a pure power law. Of course, if you are away from the phase transition and the conformal symmetry is broken, two-point functions are extremely complicated, and they contain an unknown function of the correlation length divided by the distance. But at the phase transition, the correlation length goes to infinity, and you get the pure algebraic answer. That's one constraint that follows from the conformal symmetry. Another more impressive constraint is about the three-point functions that I didn't even mention. The three-point function of three perturbations A, B, C, three operators at different locations, is completely uniquely determined by SO4,1. When you go to four-point functions, then SO4,1 is not sufficient to completely determine the correlation function. It's only sufficient for 2- and 3-point functions.
I'm sorry. Even to determine the form of 3-point correlator function, SO4,1 symmetry is sufficient. The form, mathematical form.
Yes, I can write the answer. I can write
even in 2-dimension.
Yes, I can write the answer in the chat. You get something, let's say the points are x1, x2, and x3. You get some answer, I'll write it in the chat, which is 1 over the distance between 1 and 2 to some power, then 1 over the distance between 1 and 3 to some other power, and the powers are known. I'm just not gonna write them down now.
See.
You get basically an answer that looks like 1 over the distance between 1, 2 to some power, the distance between 1, 3 to some power, and the distance between 2, 3 to some power. And each power, I'll write the formula for each power. So let's say the power that appears in 1, 2 is the scaling dimension of 1 plus the scaling dimension of 2 minus the scaling dimension of 3.
I see. Thank you.
Up to a factor of 2 that I may have confused now. Okay?
Yeah, thank you.
So the conformal symmetry has been very powerful, and it led to decades of research on correlation functions of local operators. And in fact, it's still ongoing. People are still trying to determine these numbers to a higher and higher precision, as many of you know.
But by the way, this conformal group SO4,1, you're thinking about three-dimensional Euclidean space?
Yeah, all the examples that so this example, I did not draw a picture in 3 dimensions. It meant to be the Ising model, statistical Ising model in 3 dimensions. So I'm sorry, the picture is a little misleading. Here it's three-dimensional just because it's water. Here it's 3 + 1 dimensions at finite temperature, which reduces to 3 dimensions at the critical point. And this is a lattice, which is 2-dimensional. So again, it's in 2 + 1.
Mhm.
Yeah, so all the examples I meant to present were in 3 dimensions.
Okay. So there
Right,
is a
Zohar,
question in chat about, there's a question says, is there any topological constraint?
Yeah, this is a great question. If the person asking want to elaborate what he really has in mind or she has in mind, but I can just try to guess. So indeed, a lot of the work that went into the research of local operators uses representation theory of SO4,1 and the constraints that I just mentioned about 2-point function, 3-point function, and so on. Actually, nobody has found interesting constraints from topology yet. One exception is 1 + 1 dimensions. So not 2 + 1, but 1 + 1. There, the topology of the torus was very important for historical developments. But in higher dimensions, nobody found any applications for non-trivial topologies yet. There are like small applications. I wouldn't say something impressive. Okay. So I'm going to talk about a completely different subject today. Well, it's different. I'm not going to talk about local operators. I'm going to talk about operators that in the Euclidean signature are localized on a line. This has some good meaning in the quantum case of zero temperature phase transitions. And it also has some meaning in statistical mechanics, where it's an operator that's localized on a line. So let me just, before I move on, I just want to explain what is the meaning of studying this kind of question about operators that are non-local, that are localized on a line in three-dimensional space. So if you think about it as a quantum system in 2 + 1, you can think that the line runs parallel to time. So then you're basically studying the physics of an impurity. It's not a local operator. It's like you take your sample, you add some garbage. The garbage is this red color, and the garbage has its own Hamiltonian. I just wrote some Hamiltonian that you could consider for how this piece of garbage interacts with the rest of the lattice. And this piece of garbage can have some dynamics. So in the infrared, it can be trivial, so meaning that the garbage has disappeared effectively in the infrared, or the garbage can flow to some non-trivial fixed point in the infrared. It's complicated. But the physical meaning of line operators in the quantum setting of condensed matter is that this is an impurity. The physical meaning of line operators in the high energy physics setting could be either an impurity, if you think about Lorentzian signature, or it could be just a Euclidean operator that is non-local, localized on a line. So the study of defects or the study of impurities is essentially the same as the study of extended operators. And today I'm going to talk only about one-dimensional extended operators. I'm not going to talk about 2D or 3D extended operators, just about one-dimensional extended operators, because they correspond to localized impurities. You can also imagine an impurity that's localized on a higher dimensional space. That would be like a surface operator in Lorentzian signature. So local operators are probing existing degrees of freedom. Line operators, you can think about them as adding new degrees of freedom that are coupled to the original system. So that's a very useful point of view to keep in mind. Actually, historically, this kind of defects have been very important. So I might remind you that actually Wilson came up with the renormalization group because he was thinking about a particular line defect in 1 + 1 dimensions. And also most of the pioneering research into integrability in quantum field theory came from thinking about a particular line defect in 1 + 1 dimensions. And actually also historically, the conformal symmetry arose from line defects. But there is very little work on line defects in more than 2 dimensions. And so today, this is the subject. We're going to study impurities in 2+1 dimensions, mostly. And at the end, I'll also make some comments about 3+1 dimensions. So this is the subject of the talk, these extended operators. So let me explain what is the sort of question that you even want to ask about a line operator in such a conformal field theory with SO4,1 symmetry. So
Can I
yes,
answer? So
yeah.
you basically use the notion of defect and operator interchangeably. I mean, as far as I know, defect can change the quantization in our Hilbert space, but operator doesn't.
That's an outstandingly good. So let me try to respond. Have you finished asking the question?
Yeah, so I'm just confusing the notion of operator and defect.
Yes, very good. Very good. So let me try to explain it.
Make me clear?
That's a very good question. So let's imagine that we're in Lorentzian signature. So time runs up, and space is horizontal. So space is here and time goes up. So if we put our extended operator parallel to time, the interpretation is that we have changed the Hamiltonian, because this is now something that exists at every instance in time. It's not an operator, it's a modification of the Hilbert space, and it's a modification of the Hamiltonian. If we take the same extended line operator and just rotate it by 90 degrees, then it acts at one instance of time, and it looks like an ordinary extended operator that acts on the Hilbert space. Now, in quantum field theory, there is an axiom that says that you're indeed allowed to do this rotation by 90 degrees. It's essentially the theorem of Osterwalder-Schroeder, which says that you can do a weak rotation and then analytic continuation to get real-time dynamics. So that's why in quantum field theory, the defects and extended operators are interchangeable subjects. You can either think about extended operators acting on the Hilbert space, or you can think about localized defects that change the Hilbert space in Hamiltonian. These are supposed to be equivalent because they are related by a rotation by 90 degrees of where you do how you quantize the theory. In condensed matter, where there is no manifest Lorentz symmetry, the space of defects and the space of operators which are extended are not necessarily the same. But near a phase transition, because there is this conformal symmetry and all this mathematical structure is inherited, they become the same.
Okay, thank you.
Any other questions?
For a condensed matter system, could you also say that even if it's not near the critical point, you also get the same structure between defects and extended operators if you're at the a gapped IR fixed points, you have a TQFT?
If the low energy limit of the condensed matter system is a TQFT, then you can say that.
Okay, yeah.
If the critical point is not a Lorentz invariant critical point, but it has dynamical exponent, let's say 2, then I don't think you can say that. I think that in principle, the space of defects and the space of extended operators are distinct.
Okay.
This is very clear in fracton models, by the way.
Right.
They're completely distinct spaces. But in ordinary second order phase transitions with dynamical exponent 1, they're the same because you have this weak rotation axiom.
Okay.
So therefore, I'm going to use 3 pieces of terminology interchangeably. 1 is extended operators, 2 is impurity, and 3 is a line operator. I'm just gonna say these words more or less interchangeably because they're all the same at the conformal field theory. But it's a highly non-trivial fact to even understand in a given Hamiltonian system in condensed matter why the space of defects and the space of extended operators is the same. It's highly non-obvious, in my opinion. So I just wanted to say that they have a very important role historically, these objects. And this is just an example of how you think about it in a Hamiltonian language, that the impurity has its own Hamiltonian, its own Hilbert space, and this Hilbert space is coupled in some way to the bulk. Okay. So what is the central question about line defects? What do you want to know experimentally? Experimentally, you want to know if given a line defect, if it flows to a non-trivial conformal extended operator. I'll define what it means, or non-trivial conformal impurity, or it flows to a topological impurity, or maybe even it becomes completely transparent. A completely transparent impurity means that it's just not there, that if you make any measurement, you can't see that there is an impurity. But a non-trivial conformal impurity has some interesting implications on green functions, one-point functions, and so on. So when you're given an impurity, the most important question in conformal field theory is whether it's screened, meaning trivial, or it's not screened, meaning that it's a non-trivial conformal impurity. And I just wanted to say that this kind of classification of what could happen is a little bit rough. For the more advanced people in the audience, you can also imagine that, for instance, it becomes completely transparent. So you cannot see that there is an impurity by bulk correlation functions, but still the impurity has some degenerate Hilbert space. So there could be several ground states in this quantum mechanical theory on the line defect, even if it's completely decoupled from the bulk. So if you want to say what are all the possible options, you have to be a little bit careful. But roughly speaking, you want to know if it's screened or not, meaning if you can detect the impurity by measurements at long distances in the second order phase transition. That's the simplest question you can ask. Okay, so what does it mean for a line operator to be conformal? Our group was SO4, 1. Let's put d equals 3 for the sake of this slide. So this is SO2. So our original conformal group was SO4, 1. We can say that the line defect is a conformal operator if the theory with the line defect preserves SL2R times transverse rotations. I'm just assuming that transverse rotations is a symmetry. It doesn't have to be. The most important thing is SL2R. So we say that an impurity is conformal if in the presence of the impurity, the full set of correlation functions preserves SL2R. If the impurity is not conformal, then there is no SL2R, there is only energy conservation. So energy can be exchanged between the impurity and the bulk, but there is no SL2R. SL2R contains, in addition to energy conservation, rescaling symmetry and a special conformal transformation. So when we ask about the long distance limit of an impurity, we ask, does it lead to a non-trivial SL2R invariant theory? Or is it just trivial and decoupled from the bulk? Okay, so this is the mathematical meaning of a line operator being conformal. Given a line operator, it's very difficult to know if it's conformal. It's like asking, is a quantum field theory conformal? It's difficult. So one has to do some analysis.
Wait, isn't there translation invariance along the line also?
Yeah, that's this. Hello, Kim Young. I identified your voice. This is R. This is the translational symmetry along the line.
Oh.
It's always present, even if the impurity is not conformal. But if the impurity is conformal, you also have scaling symmetry and a special transformation that looks like T going to T over 1 plus T.
Okay, thank you.
I can write it in the chat. I didn't want to write it in the slides. I think it's something like this.
Thank you.
That's what the mathematical meaning of a conformal line operator. Now, another very important thing is that in the ordinary theory of conformal field theory, we have local operators. But now that we have an impurity, it's clear from this picture that there are operators that are made out of the usual blue spins, but there are also operators that are containing the degrees of freedom of the red impurity. So therefore, the space of local operators is now a little bit more complicated. So there are ordinary bulk local operators, but there are also defect operators. These are operators that are localized on the impurity. They can act only on the impurity. And they are sitting in some representations of SL2R. Not SO4, because SO4, is broken to SL2R, but they're sitting in some representation of SL2R. And in general, the operators that act on the defect have nothing to do with the original bulk operators. They have different scaling dimensions. There are a different number of them. They're unrelated. The magic is that you can do a Taylor expansion, in quotation marks. You can take a bulk operator and approximate it as typically an infinite sum of defect operators. So the objects with a hat are operators that act only on the defect. So they're only functions of time. And these are bulk operators that existed even before we put the impurity. So you can expand bulk operators in terms of defect operators with some powers of the distance. This is a very useful expansion, like a Taylor expansion. If you have a bulk operator that is very close to the impurity, this expansion becomes very useful. Indeed, you can understand from this picture that bulk operators that live somewhere far away wouldn't almost see the defect. So who cares that there is an impurity? But bulk operators that are here could be expanded in terms of operators that act only on some effect on the red blob. So it makes sense. Experimentally, what do people measure? The main thing that is currently being measured with impurities at phase transitions is the 1-point function. So people measure the 1-point function of bulk operators. Yes?
A minor question. So why am I allowed to separate these two variables mathematically?
Can you
The
say
x
again?
Why am I allowed to separate these two variables, x perpendicular and t? It seems to me that mathematically we're allowed to separate these two variables. If you write this as a Taylor expansion, why is it obvious that it should work?
So you think about it as this is a time slice, right?
Yes.
And in this time slice, we take a point of view of, let's say, Heisenberg's point of view, that there are operators that are made out of zero from blue spins and operators that are made out of perhaps blue spins, but also red spins.
Mm-hmm.
So the statement is that the space of operators is such that you can approximate the action of blue operators in terms of operators that are red operators. And we do this expansion at a given time. It's in the Heisenberg picture.
I see.
So we don't change the time t. We expand operators at a given t in terms of other operators at a given t.
I see. Okay, thanks.
Can I ask a question?
Sure.
Can I understand your framework from the example of the conformal field theory approach to the Kondo effect, like Affleck and Ludwig?
Yes.
I mean, I'm just trying to find some connection between yours and their results. And
Yeah.
Okay, that's just a simple comment.
Yeah, I mean, that's what I meant to say here, that there has been a huge amount of work on the Kondo problem, but the situation in higher dimensions, especially in 2+1, is very open. So I'm going to tell you about results in 2+1. That's the main point of this talk. The Kondo problem has been beaten to death in 1+1. It was solved in many different ways, both from the conformal field theory idea, from integrability, from RG. But if you look at the literature in higher dimensions, almost nothing is known.
Okay.
So that's the main thrust for what I'm telling you.
Okay.
Okay. Okay, let me just make one more comment before I tell you what I'm gonna actually tell you about. This is just an introduction. Oh, I forgot to say. So the main observable that people measure, and we have some data about, is 1-point function of bulk operators. So people just measure the VEV of the order parameter. If you are at an ordinary phase transition at the second order phase transition, the order parameter doesn't have a VEV. It has 0 expectation value because you don't have magnetization yet. You're in the second order transition. But if you have an impurity, many local operators, including the order parameter in many examples, will have a non-zero 1-point function. And the coefficient that appears is what people measure experimentally. So that's one signature of a defect, that it leads to a correlation function, the 1-point function that is non-vanishing and decaying away from the defect. So when we say screened, we mean that little a vanishes. When we say that the defect is not screened, that it's a conformal defect, we mean that a is non-vanishing. So that's one mathematical meaning for these words that are used here. Transparent means vanishing a, and conformal means non-vanishing a. Okay. One last comment is that there is an important operator. This is just as a general remark, that is called the displacement operator. It's a defect operator. That's why I put a hat. It's an operator that basically moves the defect. So you can see from the lattice picture, you can ask, why did I put it here? Why I didn't put it here or here? You can even make it move in time. You can decide that your impurity or piece of garbage is moving in time. So there is actually an operator that lives on the defect that implements this transverse motion of the defect. It's a universal operator that's called a displacement operator, and it has a protected scaling dimension. The scaling dimension is the Cartan of SL2R. So another definition, if you want, for what it means for a defect to be screened is that it has a vanishing displacement operator. So if something is screened or transparent, who cares where you put it? You anyway don't feel it. So that's mathematically implemented by saying that a defect is screened if it has a vanishing displacement. A defect is not screened if it has a non-vanishing displacement. Okay, so this is the end of the introduction. Now I'm going to tell you what I'm actually going to do in this talk. So I'll discuss 3 problems. Probably I won't get to all of them. Maybe I'll finish the first one. So I'm going to discuss 3 problems, which are important line defects that are also discussed in experiment. So the first one is the localized external field in the ordinary Wilson-Fisher phase transition between a ferromagnet and a paramagnet. So usually we put a uniform magnetic field and we study the response of a magnet to uniform magnetic field. But you can also just put localized magnetic field that's only localized at a few lattice sites. And you can ask, okay, this is some special line operator. It's an impurity. It's just magnetic field through a few points. So you can ask, what is the response of the system to such a magnetic field that's localized at a few points? So it's a special line operator, and I'll discuss its infrared limit. The next problem is a little bit more complicated. It's basically the Kondo problem that people already asked about, that Hyun Lee asked about. It's essentially what this picture was about. It's some external spin with some degrees of freedom T that is coupled to the magnet. That's the 2+1 dimensional version of the Kondo model. It was beaten to death in 1+1, but I think about 2+1, essentially nothing was known. And it's something that, again, there is a little bit of data from experiment, Monte Carlo, so there is some stuff to compare with. Finally, I wanted to talk about Wilson lines and gauge theories and the infrared limit of Wilson lines, which is perhaps most interesting for the high energy physicists in the audience, but I'm afraid I won't get to it. Anyway, there is a paper out on this topic that you can look at. It's this paper, the second one. It covers everything about the infrared limit of Wilson lines. I'm afraid I won't get to it.
Question.
Yes.
I missed the timing. In the previous page, what do you mean displacement operator, DN, for impurity?
Can you please say again? I just couldn't hear.
Yeah, in the previous page, so what do you mean the displacement operator, DN?
Oh, you have, yes.
The impurity is fixed at one position. So does it move?
Okay, so you see, one experiment you can imagine is that you put an impurity at a given position. But you can imagine more complicated experiments that people typically don't do, but you can imagine them, which is that, let's say somebody moves the impurity for a period of time and then stops. So if you want to theoretically model such a more complicated experiment, you have to deform the impurity by this displacement operator. That's why impurities have such a special operator. It allows you to study what happens if somebody moves the impurity from point to point.
I see.
It usually doesn't arise in condensed matter because people typically imagine that the impurities are fixed on the lattice. But if you want to study the response of the lattice to an impurity that's hopping, then you need this operator.
I see.
Okay, so these are the actual problems that I was working on in the last 2 years solving them. And now there are also some theoretical ideas that I wanted to explain. So I'm going to talk about the first, and probably I'll skip the second because I'm afraid I won't finish. It's the question of how to even count the number of degrees of freedom that is localized on the impurity. And the second question that you can is, what are the constraints from ordinary global symmetries on the physics of impurities? Some of these systems have some global symmetries, and impurities could break those symmetries, or they could respect those symmetries. And actually, there is a very interesting discussion of what are the implications of the symmetries if they are broken, and what are the implications of those symmetries if they are preserved. But first, I wanted to discuss the question of how to even count the degrees of freedom that are localized on the impurity. You will see that this is important. It would allow us to, it would guide us in solving some of these problems. So it's an important discussion to try to define the number of degrees of freedom. Okay. Are there any questions about what I'm going to do? Now I'm going to start with this topic of how to count the degrees of freedom on an impurity. Okay, so let's go on and discuss this question. So I'm going to try to define a notion that is called that we call the defect entropy. It's a way to count the number of degrees of freedom on the impurity. And let me just describe how this is done. It's a strange prescription, but this prescription has a very nice advantage, several advantages that I'm going to explain. So first, you take the line defect and you make it into a circle. Now, for a condensed matter theorist, this makes absolutely no sense because the line defect is stretched in time. So it's a localized impurity. You cannot make time into a circle. It's a contractible circle, by the way. You just make the line operator. But if you think about it as an operator that's acting in one instance of time, it's natural to think about this operator as being extended on a circle. Okay, so we make the line operator into a circle, and we compute the expectation value. So we compute the vacuum expectation value of this circle, normalized by the vacuum expectation value of the unit operator. So this is the logarithm, and then we take the logarithm. So we compute the expectation value of the circle, we take the logarithm, and then we apply some differential operator, which is 1 minus the radius of the circle times the derivative with respect to the radius of the circle. And that defines the notion of defect entropy. Why do you need this complicated differential operator? It's because, as you know, expectation values in quantum field theory are divergent, scheme-dependent. So this guarantees that the scheme-dependent piece cancels out. So therefore, this quantity is scheme-independent, and every two distinct ways of computing it would agree. So this gives you a notion of defect entropy. It's a weird thing because it's hard to compute in the laboratory, but it's easier to compute in Monte Carlo or analytically. Now, the claim is that this defect entropy is some very useful way of counting the degrees of freedom on the impurity. Now, why is that? If you look at topological field theories, this kind of expectation value of a circle is very famous. It's called the quantum dimension of the corresponding line operator or the corresponding enyon in condensed matter. And this quantum dimension is an important observable. For enyons in topological field theories, G is bigger than 1, which means that log of G is positive, which means that S is positive. Today, I'll show you that for conformal impurities in non-topological field theories, this doesn't have to be true. So the quantum dimension can be smaller than 1, but G is always positive. So the logarithm is always well-defined, but S could be negative. So the defect entropy could be negative, but it's a real number. So I'll show you today that the defect entropy can be negative. What does it mean to have a negative number of degrees of freedom on an impurity? It might strike you as a very silly definition, but I think it actually makes sense. Because if you put the impurity, it could repel degrees of freedom. So effectively, each spin or each block carries some number of quantum fluctuating degrees of freedom. But if the insertion of the impurity pushes away the support of the wave function of the ground state, you could say that due to the impurity, there is a negative number of degrees of freedom in some big block here. So the defect entropy could be negative. This makes perfect sense. Of course, in topological field theories, there is no bulk degrees of freedom. So it makes sense that the quantum dimension is always bigger than 1, and the entropy is positive. But for conformal defects, it might be negative. Okay, so this is the notion of defect entropy. Why is this notion useful? This notion is useful because it satisfies a very non-trivial inequality. If you take a derivative of the defect entropy with respect to the size of the circle, it's a monotonically decreasing function as you increase the radius. And this leads to a new result similar to the A theorem. It means that the quantum dimension at short distances must be bigger than the quantum dimension at long distances. This is always true for any line defect in any number of dimensions, and it's also true in 1+1 dimensions. So this is a completely general constraint on the number of degrees of freedom of every impurity in every number of dimensions. This has many implications, and I'll show you one implication for magnets. So you'll see that for this problem of localized magnetic field in the Wilson-Fisher phase transition, this has very interesting implications, this inequality. So let me just say what type of implications. If you assume by a contradiction that your line defect is screened in the infrared, meaning that it's completely transparent, that means that its quantum dimension in the infrared is 1, because it's the unit operator in the infrared. But then, because of our inequality, it means that in the ultraviolet, the number of degrees of freedom is bigger than 1. The quantum dimension is bigger than 1. Typically, the quantum dimension in the ultraviolet is very easy to compute because everything is weakly coupled. And we will do this computation in the magnet, and we will see that there is a contradiction. So just this inequality implies that the external magnetic field in the ferromagnet-paramagnet transition cannot be screened. It has to flow to a conformal defect with a negative quantum dimension. So negative defect entropy, I meant, with negative defect entropy, meaning G smaller than 1. Similarly, if you assume by contradiction that the infrared is a transparent line, but with H degenerate states on the line, you would reach this inequality, and this can be sometimes contradicted by an explicit computation. So the application of this theorem is very similar to C theorems. You sometimes can rule out simple scenarios based on this inequality, and we will see an example today. Are there any questions about the defect entropy and the monotonicity of the number of degrees of freedom on the defect?
Joe, can I ask a question?
Sure.
So for
Hi.
this monotonicity, are you assuming that bulk theory is topological or CFT?
Anything, it always works.
Oh, I see. For any bulk theory, it works.
It has to be either topological or it has to be CFT or topological. It's not true for massive quantum field theories.
Okay, yeah.
I don't know what happens in massive theories. I'm talking about the impurities in the second order phase transition. So the phase transition could be a topological theory, it could be a conformal theory, and then it would be true. But I actually don't know what happens in massive theories.
So here you are assuming that bulk theory is at the second order phase transition.
Yes.
Okay, thank you.
Then also this is true. You see, if this is not true, then this is not true. This is not true. Everything I said is not true if you're away from the conformal fixed point in the bulk.
Okay, thank you.
Thanks for the clarification. If this wasn't clear, then I should have made it clear. This is at the phase transition. These are impurities at the phase transition. Like in the Kondo problem. Also in the Kondo problem, the most interesting case is when you insert it at the mathless point. Any other questions about this business? Good. So I'm going to skip the discussion of what are the implications of zero form symmetries. I'll return to it at the end if I have extra time. I had a few comments about it, about the interplay with topology and projective representations and so on, but it will take me too far afield. So I'm going to skip it. I'm just going to summarize what I told you about the number of degrees of freedom and the impurity. So the degrees of freedom on the impurity are reduced as we flow to the infrared, and this leads to rigorous inequalities. And now I'll show you how to apply it, how we can usefully apply this inequality for a problem of line defects in the Wilson-Fisher fixed point. So that's and here we'll compare with experiments and call it a day. So I will discuss the Wilson-Fisher fixed point. I'll be mostly interested in 2+1 dimensions, but just for the sake of entertainment, the number of dimensions will be between 2 and 4. And what do we do? What is the line defect? The line defect is an integral at x equals to 0 over the first component of the order parameter. So remember that the order parameter in the Wilson-Fisher model is a vector phi. It's this Itzikson-Zuber large N model, or finite, or the Wilson-Fisher model basically, with a vector with a vector phi as the elementary degrees of freedom, and we just integrate phi1 and we add it to the action with some coefficient h. So you can think about it as a line. If you like the language of Wilson lines from high energy physics, you can think about it like I'm writing in the chat. It's essentially like a scalar Wilson line that is very familiar to people that do supersymmetric gauge theories. It's essentially like I wrote in the chat, it's the exponential of the integral of dt phi 1. It's what in high energy physics people call a scalar Wilson line sometimes. So you want to know what's the infrared limit of this object in the infrared. Sorry, what is the infrared limit of this external magnetic field with coefficient h? Okay, so it turns out that this coefficient h is a relevant perturbation. It's because the scaling dimension of phi 1, if you remember some things about the Wilson-Fisher model, you might remember that the... Yes? Hello, Sanjay. Yes?
No, it's not a question, sorry.
Oh. If you remember the Wilson-Fisher model, the scaling dimension of phi 1 is roughly speaking a half near 3 dimensions, but it's always smaller than 1 in this domain. In this range, it's always smaller than 1. So this perturbation is actually relevant for across these dimensions. It's a relevant perturbation for any n, and therefore the ultraviolet quantum dimension of this line operator is just 1, because in the ultraviolet, h vanishes. And therefore, using our logic from before, we see that this leads to a contradiction, because the ultraviolet quantum dimension is 1, because it's an asymptotically free line defect. So it cannot be 1 in the infrared. And therefore, this immediately implies that an external magnetic field in the ferromagnet-paramagnet transition cannot decay at long distances, and it leads to a non-trivial conformal defect with a negative defect entropy. or G smaller than 1. So to summarize, the external magnetic field cannot be screened and cannot disappear. So similarly to Wilson lines that people are very familiar with from the high energy community, this scalar line operator is not trivial. That's what I'm saying. It's a conformal line operator. It's non-trivial in the infrared. Very much like the Wilson lines that people study in n=4 super Yang-Mills. Okay. Now about this localized magnetic field, there are many experiments, in fact. And it seems that simulations and experiment are consistent with what I'm saying. It's an infrared stable fixed point. The impurity is an infrared stable fixed point, obeying SL2R symmetry. And one can try to compute its properties. This is confirmed by many simulations, some of them very recent. Most of them are very recent, and experiments. So let me tell you what can be done about this problem. We've spent some time trying to solve it, to generate predictions. So of course you can solve the large N limit. This leads to a complicated Schwinger-Dyson equation that we wrote down, but we could solve it only in some limits. So it's maybe requires a little bit more diligent work to give a complete solution of this problem at large N, but we did the first baby steps. We wrote the Schwinger-Dyson equation and found a consistent ansatz. Near 4 dimensions, you can do epsilon expansion, and here you really cannot do very much. I mean here at in 3 dimensions at finite N. Near 2 dimensions, there is probably some kind of 2 plus epsilon expansion, but we're very confused about it at the moment. Anyway, so there are exact results at large N and some epsilon expansion results. So I'll try to show you what they converge to and compare with experiment. And you'll see that indeed the general predictions that follow from the G theorem are correct, and it leads to a conformal line operator. So I'm just giving you an example of the epsilon expansion results. So already in the epsilon expansion, you can see that the defect entropy is negative, unlike anyons in TQFTs. So this is the leading order in epsilon prediction for the defect entropy. And this is the leading and subleading predictions for the scaling dimension of the defect operator, phi 1. So it's the magnetic field. It's the operator that couples to the magnetic field, but only on the impurity. It has a different scaling dimension from the magnetic field in the bulk. Okay, so these are results from the epsilon expansion. And as I said, one can also do the large N limit. Here I wrote the line operator in a more familiar language to high energy physics. It's just a scalar line operator. It admits, quite surprisingly, a very smooth large N limit. Even though it's just one component out of an N vector, it admits a very smooth large N limit with a 't Hooft coupling. And you can just find the classical solution. Honest to God solution of the Schwinger-Dyson equations, which corresponds to a new classical action. And this has appeared in many recent works in various other applications. So people found the same in many, many other models for surface defects and line defects. It seems to be a very general idea. And these are the predictions from the exact large N solution. Indeed, we see an exponentially small defect entropy, exponentially small quantum dimension. So it's certainly smaller than 1. It's exponentially small, and the defect entropy is very negative. It's in fact linear in N. And the scaling dimension of the operator that couples to the magnetic field is huge. In the bulk, it's 0.5, as I told you, give or take. It's 0.51. I actually gave it before. It's 0.51 something here. This is the bulk scaling dimension. But near the defect, there is a huge renormalization of the scaling dimension of this order parameter, and it's 1.5. That's what we found in the large N limit. Okay, now let me show you the experiment. So many people have simulated this model, and there are some experimental measurements, and they roughly all agree. You do find something like 1.5. So I think it's on the right track. It seems that there is some agreement. Recently, there was a very important analysis by these collaborators, Huche and Zhu, and I think They have some small disagreement with some epsilon expansion results, but I think that after you do some Paderi summations, this disagreement will go away. So roughly speaking, everything seems to be on the right track. So this is the first example that I wanted to show you of this scalar line operator. Yes.
Can I ask a quick? So what happens with correlators? Have you computed correlators?
What kind? Like which ones would you want?
I think you can tell. Well, any correlator of you showed us 1-point functions are kind of have the structure you showed us, probably, right? And
yes,
then I would be interested in displacement operator correlators.
So this coefficient, we computed it at large n exactly for the decay of the order parameter, like the polarization of the spins away from the impurity. We have an exact answer at large n.
For which operators? Yes.
For phi 1. For the displacement operator.
Yes, that's
I don't think we know the answer to that. No.
Or stress tensor, there are many things you can do.
No, we didn't try. We don't know. Actually, the displacement 2-point function is an interesting observable that you bring it up because of the connection that you're probably familiar with to the Bremsstrahlung function. So yes, you're right. It's something that can be even tested one day, but we didn't try to do it. No.
Right. Thanks.
Any other questions before I move to the next, to the actual Kondo problem? I just wanted to show you the example of the Kondo problem, and then I won't go into gauge theory. It's too much. I think I would lose everybody by this point. Okay, so let me just tell you what is. So here, this is a scalar line operator. You could say it's a little similar to what you encounter in gauge theories, but the next example, which is also in magnets, is even closer. So let me show you. So here, I'm going to specify. I'll concretely study the O3 Wilson-Fisher model, which describes the real life ferromagnet to magnet transition. But now, instead of turning on an external magnetic field, I'm going to put a red blob on the spin chain, on the lattice, exactly like in this picture that I kept coming back to. So we put a red dot, which has internal spin S, while the blue dots have spin 1/2. And the way we couple the bulk to the line defect is through this ordinary coupling, like in the Kondo problem. We couple the S operators that live on the defect to the bulk order parameter, and the coupling constant is gamma. So this leads to a line operator, which is even more similar to things that you know from gauge theories, but this is again in magnets. Phi A is the order parameter of the Wilson-Fisher model, and SA is the spin operator that lives in SO3. And we take the representation, we take the spin operator to be in the 2s plus 1 dimensional representation of SE2. And then we do a trace of a pass-ordered exponent. Beautiful, exactly as we do in gauge theory, but there is no gauge field. So the question is, what is the infrared of putting such an external spin in a magnet? This could be some external atom or something of that sort. And about this, experimentally, let me just tell you, experimentally, we don't yet know really what happens for small values of the spin. People believe that it's conformal for all values of the spin. That's I would say, the state of the art in experiments and theory papers on the subject. So let me just show you what can be done about this problem. Here, there is some aspect that I don't have time to cover about the fractionalization of degrees of freedom. I might come back to it if somebody wants to hear about it, but I'll just tell you that you can do some sort of epsilon expansion. It's very complicated in this theory. And you can do some kind of effective field theory analysis for a large spin. It turns out that when this external spin is very large, you can do a semi-classical limit. This is maybe a familiar idea that when the quantum numbers on the line operator are very large, you can do a semi-classical limit. So we found such a semi-classical limit. We solved it exactly. And we also solved some epsilon expansion, and everything seems to point to the fact that all the way to spin a half in 2+1 dimensions, which is the physically relevant case, the thing is conformal, so it's not screened. This is different from the Kondo problem, where the experts in the audience might remember that in the Kondo problem, it was screened for small enough spin, but here it's not. It seems that it's not screened. So this is our prediction. And there is a lot of recent work on this model. You can look up some of these papers. And more or less, I can summarize here. I have a huge amount of additional material to explain, but I'm afraid that it's already too much. So maybe if somebody in the audience wants me to talk about something in addition, I can, or I can just summarize here. So just let me know, what do you prefer?
We still have a bit of time, so.
Okay, so maybe I'll just tell you about the main properties of Wilson lines. I'll just spend, let's say, 10 minutes at most. I'll just give you the upshot of what is the physics of Wilson lines in conformal gauge theories. So Wilson lines represent a very special type of impurity. It's different from the impurities we studied so far. So far, we coupled spins to magnets, or we put an external magnetic field. Wilson lines represent a more interesting class of impurities where they're charged, right? It's electric charge. It's some huge massive particle with electric charge in some representation R of the gauge group. And we deform the Hilbert space by putting it, let's say, at x equals to 0. Now, usually people discuss Wilson lines as order parameters for confinement, deconfinement, but that's not the subject here. I'm interested in conformal field theories, and I'm asking if the Wilson line is a conformal line operator preserving SL2R or not. So let's take massless scalar QED. That's like a toy model for a conformal theory. Of course, the experts know it's not exactly conformal due to the Landau pole, but that doesn't matter for the discussion today. So let's take a scalar, a boson coupled to a gauge field in 3+1 dimensions. And this represents an external charge, Q. So this problem is basically the hydrogen atom, because this external charge, you can think about it as the nucleus. So what is the saddle point of this funny classical action? It's just a Coulomb field with a vanishing scalar field, of course. That's just the hydrogen atom. But it turns out that this actually is not completely correct, surprisingly. So if you assume that this was correct, you could compute the scaling dimension of the bilinear gauge invariant operator as a defect operator, and you find this answer with a square root. So the scaling dimension of phi dagger phi as a defect operator is 2 away from the defect. That's the scaling dimension in scalar QED. But due to the defect, it has the square root, and it becomes imaginary at some point. So if the if the external charge is too large, there is some sickness. What is the physical meaning of the sickness? If the electric field that the nucleus creates is so large, it can create pairs of phi dagger phi by some sort of because it destabilizes the vacuum. So you put this line operator, but it turns out that it might not be conformal because it leads to a cloud of phi particles, and the charge might be screened. It might even be trivial. So how do you analyze this question? One way to think about it is that Wilson was kind of wrong. He forgot to add another term to the Wilson line, which is a gauge invariant phi dagger phi. This is an important operator because, as you've seen, its scaling dimension becomes 1 when the charge is exactly satisfying this equality. So when E squared Q over 2 pi is exactly 1, the square root vanishes, and phi dagger phi becomes a marginal operator on the defect. So writing the Wilson line without this phi dagger phi is inconsistent. At least for large enough Q, it's inconsistent because there is a marginal operator. So you have to compute the beta function. And that's the answer that you get for the beta function for this operator. For small enough charge, there are actually 2 conformal Wilson lines. not 1. And I maintain that the same is true in n equals 4 super Yang-Mills. So there are 2 fixed points for the Wilson line. As you increase the charge, the 2 fixed points go into the complex plane, and the coupling runs to strong coupling, and you have to analyze the infrared limit. So for large nuclei or large charge for the nucleus, the coupling runs to infinity. This effective coupling G runs to infinity, and you have to analyze the infrared limit of the Wilson line. So this is very similar, we think, to how QCD goes to strong coupling and breaks the chiral symmetry and confines. And we found some similar answer here. We found that this impurity generates a dynamical scale, which, so let me just put it in terms of numerics. In real life, the fine structure constant is 1 over 137. So if you put a nucleus with charge 137, we find that this is true, that this becomes imaginary, and the vacuum is destabilized. What does it mean that it's destabilized? It means in the RG language that the coupling goes to infinity. And what happens when the coupling goes to infinity? What happens is that we think that there is a new soliton with a new dynamically generated scale. So there is a dynamically generated scale exactly like in QCD. And this is the soliton. We found it numerically. So close to the nucleus, you observe 137 units of charge, or Q units of charge. But as you get further away from this nucleus, and look how far you have to go, all the way to the moon, the electric field decays essentially to 0. And the scalar field has some funny profile. The scalar field has this funny profile. Initially, the scalar field vanishes, like in the hydrogen atom problem, but then it kicks up and then it goes down to 0 again. So what is the message? The message is that Wilson lines in massless gauge theories have a complicated phase diagram. For small representations or low charge, there are multiple fixed points, like in this blue line. As you crank up the charge, the fixed points disappear and go into the complex plane, and you have strong coupling dynamics. The strong coupling dynamics generates a new dynamical scale, which is numerically huge compared to the size of a typical nucleus. And this leads to a new soliton, which completely screens the charge. So if you make a measurement of what happens at infinity, you find that essentially there is no charge. So if you make a big Gauss sphere, you will say that there is no nucleus, no charge. So that's a very nice demonstration of the idea that some line operators can be screened. So you put this nucleus, but eventually there is nothing. It's completely transparent and trivial. Are there any questions about it?
Yeah, so what about running of the coupling constant? Isn't it going to 0 also? I don't know what it plays a role here.
This coupling constant runs. Oh, you're asking about the QED.
Yeah, QED coupling constant goes
Yeah,
0.
yeah. So, okay. So yes, I said, so one way to not discuss this question is to do the same in equals 4 super Yang-Mills. And everything I said, everything I said is true in n equals 4 super Yang-Mills. The Wilson lines in high enough representations are. In QED, you also don't really have to discuss it because you can notice that this combination E squared Q appears in all the formulas. So you can take a limit where E squared Q is fixed, but E squared is very small. So then this formula is exact in this limit. So you can do some kind of double scaling limit in which the running of the coupling constant is a subleading effect.
Okay, thank you.
All right. So what is the
question?
So
why? So I didn't follow. Why do you introduce the second term in the Wilson line? P take
okay. Yeah, I was very quick about this, so I apologize. When we say that the Wilson line takes this form, what do we mean? We mean that we have a charged Q particle at the origin. Okay. What does this charged Q particle do? It creates an electric field and no scalar field to first approximation. That's what happens in the hydrogen atom. right? We have electric field, but all the rest is zero.
Yes.
Now, it turns out that this ansatz is not consistent. Why is it not consistent? It's not consistent when E squared Q is too large. It's not consistent because if you compute the scaling dimension of defect operators as a function of V squared Q, you find this formula. It's an exact formula. And you see that it becomes imaginary when E squared Q over 2 pi is exactly 1. So beyond this point, there is some sickness. Okay. What is the renormalization group interpretation of the sickness? The renormalization group interpretation of the sickness is that when we wrote the formula for the Wilson line, we forgot to add another term. Like in quantum field theory or in quantum many-body systems, if there is a marginal operator that is protected by all the symmetries, we must add it. Do you agree?
Yes.
Yes. Now, why Wilson did not add phi dagger phi, why people usually don't add phi dagger phi to the formula of the Wilson line? They don't add it because it's irrelevant. So G goes to 0 in the infrared. However, the point is that for large enough Q, it becomes marginal. Which Q? When E squared Q is of order 2 pi. When E squared Q is of order 2 pi, this operator becomes marginal, and you cannot neglect it anymore. So you must add the running of this coupling to the... You must consider the beta function of this coupling. It will be generated on the Wilson line, whether you want it or not.
In the large Q case, Q of the Wilson line.
Yes. So the scaling dimension of this operator is this formula. So if E squared Q is very small, we neglect the second term, and it's 1 plus 1, so it's 2. And it's irrelevant. We don't care. But when E squared Q over 2 pi becomes close to 1, it goes to 1, this formula, and then it becomes marginal.
Okay.
You see? So we must add this coupling. And this coupling changes the phase diagram of Wilson lines. It means that Wilson lines that are subcritical have multiple fixed points because there are multiple values of G that lead to a fixed point. Actually, this is some new conformal line that you can find. And then G becomes marginal. That's the red line. And then you get this sick situation where G has no fixed point. Instead, it runs to strong coupling. And then this is where we get this new soliton that screens the Wilson line completely.
In the previous Kondo effect calculation case, Bojoni Kondo effect case, does such an operator appear? I mean,
in which theory?
In the previous Kondo effect calculation, Bojoni Kondo effect calculation, you calculated the ordered exponential SP, this line operator. So in this calculation, such an effect does not exist. I mean, to introduce some additional corrections.
Yes, it's an excellent question. You could worry that phi dagger phi, which is irrelevant, becomes important on the defect. We check this carefully. It doesn't happen. It doesn't happen for any value of little s. So if you put this external spin s, this phenomenon doesn't happen. And this formula remains correct. But in the case with electric field, where there is a charge impurity, it's completely generic that it happens. It happens in every 4-dimensional gauge theory, including QED and n equals 4 super-Young Mills. And it also happens in 2 plus 1 dimensional fixed points, deconfined critical fixed points. I have one little transparent, slide about it, that you have a similar screening phenomenon, but now the screening is for charges that are smaller than an F over 2. So this is like in QED, 2 plus 1 dimensional QED, with an F species of Dirac cones. This is the critical charge that is not screened. This could be experimentally tested in Herbert-Smith type, for instance. But yeah, so I think it's different indeed, you're right. This doesn't happen in the magnetic field problems that we looked at. It happens only in this charged impurities. I don't know why, but it's the fact of the matter.
So you mentioned that this thing also applies for n equals 4, super Yang-Mills theory. That if your defect or Wilson line has one form charge, then that is not typically screened. So
Yes.
you make that to be screened as well?
Yeah, you're absolutely right. 1,000,000%. So if you want to be super rigorous, take SO3. So what I say is true for SO3. SO3 gauge theory. Now, if you do SU2, you're 1,000,000% correct. There is a subtlety with the one-form symmetry. I don't have slides about it, but I removed them. I thought I would not have time to cover them, but I'll tell you what happens.
Okay.
What we believe happens. We haven't proven that. So one-form symmetry prevents Wilson lines in half-integer representations from being completely screened. So on the other hand, we have this calculation of the soliton that we did. And in the soliton, we check the electric field goes to 0. So we actually spent probably a year thinking about what the hell is going on. And there is a similar contradiction in metals. There is something in metals that is called Friedel oscillations, which is what happens when you put a nucleus with some charge that's not divisible by the elementary charge. And the question is what happens? Okay. We now believe that for the half-integer representations, the blue line doesn't go to 0. So there is some kind of scalar Wilson line that survives at long distances, and this somehow saves the one-form symmetry. We believe that the electric field goes to 0 at the moment, but the blue line doesn't go to 0 for half-integer representations. And somehow it saves the one-form symmetry. But frankly, if you look at the paper that we wrote on it, there is a whole section about it, like 10 pages, with various results on this subject, and we don't have a conclusive answer. We don't have a conclusive answer for what really happens for SU2 in half-integer representations.
All right, thanks.
In massive gauge theories, not massless gauge theories, in massive gauge theories, your initial intuition is 100% correct. You just get 1 unit of electric field remaining, or a half unit, and that's it. This is what happens in metals, which don't have a Fermi surface. This is what happens in the massive gauge theories. But in massless gauge theories, it actually does go to 0, the electric field. So our only hope is the scalar line survives somehow.
Yeah, very interesting.
Yeah, so this is extremely unconclusive, and I'm extremely unhappy about the situation of that question. Because we don't really have an answer, and we spent a huge amount of effort trying. So I don't know what's going on. Any other questions?
Not in this part. I mean, in the previous 2 parts, you skipped some symmetry part. Fractionalization, projective representation. Can you mention more about that part? Sorry.
Yeah, I can tell you what is the point. So I'll just tell you qualitatively what is the point, what is the idea. So when you think about an impurity that couples to a gapless bulk with symmetry G, there are 2 options. One is that the symmetry is broken in the coupling between the impurity and the bulk, and the second option is that the symmetry is preserved. Okay?
Yes.
Now, in the situation that the symmetry is broken, there is a very interesting corollary that you can make, which is that if the symmetry is broken by the coupling, there is actually a protected operator on the red line, on the red impurity, which corresponds to moving in the space of couplings that break the symmetry explicitly. And this operator is called the tilt operator. Let me just show you how this word is. What word do I mean? I'm probably mispronouncing it. So where did I write tilt? T. So there is a special operator with scaling dimension 1. It's a little similar to displacement, to be honest. Displacement takes care of the explicitly broken translations, and the tilt operator takes care of the explicitly broken unitaries. So there is a special operator on the red line that takes care of the explicitly broken unitary. It's called the tilt, and it's protected. And okay, the second situation is when the coupling between the red dot and the bulk preserves the symmetry. Then there is no tilt, but there is something else going on. So you can ask, what happens to defect operators? If the symmetry is preserved, are they in representations of the symmetry? Usually we say that bulk operators are in faithful representations of the symmetry. But what about defect operators? So defect operators are in representations of the symmetry, but there are more exotic operators that are defect changing operators. So they change one defect to another defect. They could even change the trivial defect to your defect. So these are called defect changing operators in high energy physics. In condensed matter, they are called quench operators because they implement a localized quench. So for quench operators, it's not clear that they have to be in linear representations of the symmetry. It's not clear at all. There is no reason why they should be. And indeed, if you do the analysis of examples, you'll find that defect changing operators are generally in a projective representation of the symmetry. And this leads to very interesting constraints on our G flows, actually, that these projective representations cannot disappear as their G flow evolves. But I had no time to talk about it. But that's essentially the point.
Let me explain this way. If I consider some multi-channel Kondo effect, which gives rise to some conformal and also some Meyer-Fermion some excitation appear at the impurity site as a fractionalized excitations. So can I cast that problem in this context?
Yes.
Because so can you elaborate that some more? I mean, what? Yeah, how?
So, for instance, you can study the Kondo defect in SU2 level 1.
Yeah.
And this is very similar to this, you agree?
Mm-hmm.
It's very similar to this. But since the bulk operators are in spin 1 representations of SU2, and the impurity could be in a spin 1/2, that leads to fractionalization because the bulk transforms in faithful representations of SU2 times SU2 mod Z2, but the impurity may transform in representations of SU2 times SU2, not mod Z2. So this leads to a fractionalization of defect changing operators. And this leads to constraints on our G flows, even in the Kondo model in 1+1 dimensions that people studied to death.
I see. Let me consider more about that. I think I have.
Yeah, that's what I wrote on this slide, but I haven't elaborated on that.
See. Okay, thank you.
Okay, I think I ran out of time officially. I see one question in the chat. Can you say something about interactions between two defects? Well, I have nothing to say about it here in my slides, but there are papers about it. So whoever asked this question, if you send me an email, I'll send you papers. People try to analyze what happens if you put two impurities at some distance from each other, like two red points at some distance, and try to analyze the renormalization group evolution of two impurities. So if you're interested, I can send you some references. Okay, that's all, I guess.
So maybe you can show us a summary slide or the final.
I don't have a summary slide.
Oh, okay. All right, then thank you for a very interesting, inspiring talk, and let's thank Zohar.
Thank you very much for listening, and have a great day.
Yes. So any before you log out, any comments or questions from the audience? Kim Young, do you have something to say?
So can you elaborate a little bit on fractionalization of defects?
Yeah, I can elaborate on this a little bit. So you see, when we say that the QFT has symmetry G, it means that the gauge invariant operators transform in some faithful representation of the symmetry G. Okay, so G could be SO3. So it means that the theory has no gauge invariant operators that are in half integer spin representations. Only integer spin representations are allowed. But now let's say we have a line operator, and the line operator can end. So it has an endpoint. Okay? Is the setup clear, Kim Young?
Oh,
Yes.
Yeah.
That you have a line operator with an endpoint.
Yeah.
So you can ask, is it guaranteed that the endpoint transforms in a representation of SO3? And the answer is no. For many line defects, the endpoint would transform in a representation of SO2. That's not a representation of SO3. So let me give you a simple example. I mean, it might not be the most familiar example in this context, but so in the Wilson-Fisher model with the O3 symmetry, all the operators have integer spin in the SU2 sense. But if you add an external spin a half, so you just add a qubit and you couple this qubit to the bulk in this way, where SA are the 2x2 matrices in the spin a half representation, then the endpoint operators now are not in representations of O3, they're in representations of SU2. So that means that the endpoint operators are fractionalized. They're not in representation, they're fractionalized because they're not in a representation of the symmetry of the bulk. They're in a representation of a cover of the symmetry. This looks like just a mathematical curiosity, but it has far-reaching implications for our G flows. Why? Because if such a line defect flows to something completely trivial and dumb, like the unit operator, it's a contradiction. Because the unit operator does not have to end on fractionalized excitations. The unit operator can end on one. So that immediately implies that these line operators cannot be completely trivial in the infrared. They have to flow to something that ends on fractionalized excitations. So even this small idea from topology leads to constraints on our G flows.
Okay.
Let me see if there are more questions. Okay.
Any other further questions from the audience? All right, then let's formally end the colloquium. And thank you, Zohar.
Thank you very much, everybody.
Thank you very much.
Thank you very much.
Also, Jaewon, thank you very much.
No problem. Yeah.
감사합니다.
감사합니다. Okay. Thank you.
I'll disconnect now. Have a great day.
Thanks, you too. Bye.